Welcome to lecture 9. So today we'll define semantics of expressions of PL0. We'll take a subset and look at it in some detail before we go on to other things. So let me also briefly recapitulate the notion of transition systems and so on, which we're going to use for this. So a transition system is just a collection of configurations along with a binary relation called the transition relation, and the transition relation really tells you what is possible, not necessarily what actually happens. Yeah. This, and we could regard a transition system as some kind of an infinite directed multigraph in general. We could define initial states, final states, final configurations, initial configurations, and so on, and enhance the distinguishability power of a transition system. So a terminal transition system would typically have a collection of terminal configurations, which are a subset of the configurations. You could also decorate the transition system further depending upon the use you're putting it to. You could, for example, define labeled transition systems, which in addition to being transition systems have a collection of labels associated with them. This would correspond to labeled infinite directed multigraphs. So the arcs have labels on them. And the transition relation therefore is a ternary relation, and we would typically, if L is a set of labels, then you would say that gamma can move to gamma prime on A. Okay, so the question of so all these, the notion of a configuration, the notion of labels, is loosely specified. In fact, they're really undefined terms, and that's in fact what makes the whole structure generally applied. You could interpret the notion of a configuration to suit your convenience. You could interpret what constitutes a label to suit your convenience, and that's what makes transition systems a very general method, a general tool, if you like, a general mathematical tool for specification. Yeah. So you could also define, so you could enhance these things further. You could define terminal label transition systems. You could define label transition systems with initial configurations, terminal label transition systems with initial configurations, and so on. Right? But the basic idea is that of movement from one configuration to another, and depending on your distinguishing capability, you could enhance or decorate them with more constraints. Yeah, so we already saw one example of context-free grammars represented as a transition system with a rule which really says that it's a context-free rule of replacement. Okay, for any beta and gamma, if A goes to alpha as a production in the context-free grammar, then B A gamma goes to B alpha gamma. We'll use this notation, which actually comes from, well, it comes from logic, but the way to look at it is as a production, as a rule which gives a hypothesis and what you can conclude. So if A arrow alpha is a production in the production set, then B A gamma arrow B alpha gamma is a step in a transition, yeah, or in a derivation. Yeah, so we also looked at the towers of Hanai problem. So here in this case we saw how a particular execution of the towers of Hanoi problem would look like, a particular execution. Okay, so that is specifying the runtime behavior of an algorithm. So this really specifies the runtime behavior of some particular algorithm which is actually unspecified. Okay, so it's like it's an execution behavior, and you use the transition system to define the execution behavior of some algorithm or a whole class of algorithms which support this possible sequence of transitions. Yeah, not all correct algorithms for the problem might actually support it, but there is a whole class of algorithms which support this. So what we'd like to do is abstract away the essentials of what allows these transitions. So the problem of what as opposed to the problem of how is what we want to abstract away by the rules. So the problem itself can be stated as a collection of rules. The execution behavior can be stated as a collection of rules. Given an algorithm, you can follow its execution and represent that execution as a transition system. Given a problem, you can look upon the problem also as a transition system, provided you give suitable rules. Yeah. So this is not one possible solution of the towers of Hanoi problem, because the problem itself is to design an algorithm which will allow you to move n pegs from one tower to another. Okay, so the problem is just that given this initial configuration, how do you get this final configuration? And it's not, and this is just one possible solution, one possible execution of a few algorithms, right? So the actual rules themselves of the problem, which again do not constitute an algorithm, they constitute a statement of the problem, is given by this, right? So which essentially say that you can move the peg on the top of a tower to an empty tower, to one of here there might be two towers might be empty, and so you could move the peg to either of them. Okay, similarly, if the top of a tower, so if A is less than B and A and B are on different towers, then you could move A on top of B. And this also includes the fact, these two rules together include the fact that if you have Si A, Si plus 1 B, Si plus 2 C, where A is less than B and A is less than C, then you could apply any of these two rules and put A either on top of B or on top of C. Okay, so our transition systems are inherently non-deterministic. Okay, so and that's because the transition relation is really a relation and not a function. Okay, if it's a relation, then if it were a function, then the possibility of a configuration moving to two distinct configurations would not be allowed. But the main point is that many problem statements, if you notice, the execution that we have chosen is one possibility out of a variety of different possible executions. Okay, for a whole class of algorithms. And so as a result, and moreover, non-determinism, at least in a large part of computer science, is merely a form of underspecification. An underspecification in the sense that you are not extremely concerned sometimes about whether you pursue one path or another. Right? In the statement of the problem, it does not specify to you that from the tower I, a peg can be moved only to tower I plus 1. It cannot be moved to tower I plus 2. Nowhere in the problem is that stated, and it's never stated. So as a result, the problem statement itself is such that it is underspecified. So that it allows you a variety of possible solutions, and so non-determinism is an implicit fact of life in any kind of succinct problem definition. In many cases, it's also a fact of life of the solution, because you are interested sometimes not in what order you perform certain things. So if I asked you to find all the prime factors of a number, then for example it doesn't matter if the number has several, is say some 2 to the power of 4 multiplied by 3 to the power of 6. It really doesn't matter in what order you find the 4 2's and the 6 3's. So you could define a solution in which you find a first 2, and then you find a first 3, go back, find 2 more 2's and find 3 more 3's. The fact that you write an algorithm in a deterministic programming language such that it might first find all the 2 factors, it might just factor out all the 2's and then start with all the 3's, but that's just one possible solution. And there's nothing to prevent you from having found a 2 and then finding 3's and then go back to finding some 2's more. Right? So even your solution space could be non-deterministic depending on the level of detail you want to put in. So non-determinism is an intrinsic fact of life, both of problems and of classes of solutions for the problem. So the problem statement in the case of towers of Hanoi is clearly non-deterministic, right? Because it allows the application of one of 2 possible rules at each go. In fact, if it so happens that one tower is empty and another tower has an element B small at the top which is larger than A, then any of the 4 rules could be applied, maybe any 3 out of the 4 rules could be applied, or rather I'm sorry, that's wrong. At any time 2 out of the 4 rules could be applied. So in that sense it's distinctly non-deterministic. Yeah. So if you were to generalize the problem to include many more towers, for example, then you might at some point find that all 4 rules could be applied, but you always choose one possible rule. But that's not a unique solution, right? So however, the important thing is that since transition systems are a general formalism, they allow non-determinism. However, our programming languages are deterministic. All the programming languages that you use are intrinsically deterministic, which means in your semantics you have to be able to show that there are only deterministic behaviors. For a given program, there is only one possible behavior, and showing that means that proving that your transition relation is a function. Okay, so and very often this is something that you will have to show by induction on the structure, because we are going to use the syntactic structure to a great extent. Yeah. The next important thing that I said was that whenever you specify rules, you specify what might be loosely termed positive rules and no negative rules. I mean, you never specify what cannot be done, what transitions are not possible. Whatever transitions are not possible is inferred by default. If you can prove that with the existing rules it's not possible to get a transition of this form, it's always inferred, it's not something that is specified. Okay, so you always specify what are, I mean, they are usually called positive rules. I mean, you don't specify what cannot happen. Right. So now let's look at the expression language of PL0. Yeah. So I had previously given this syntax which I called was ambiguous, but now I don't care. Okay, let it be ambiguous. What I am interested in are a collection of trees rather than actual expressions. It's just that in order to be able to write them out, I might have to write them out as expressions, maybe use brackets, whatever. But really what I am interested in is a collection of trees. Okay, so what we'll do at this moment is that so we'll deal with this. I mean, with these operators, however ambiguous they are, we know how to get rid of ambiguity for the purposes of parsing and compiling and so on and so forth. But we are interested in specifying a semantics which is not cluttered up with all those non-terminals which do not have great semantic significance. So we'll deal with this ambiguous grammar, but whenever we write an expression, it is understood that we are writing not an expression but a tree. Yeah. So we are really interested in the syntax trees in an abstract form, and we are not really interested in the what might be called the lexical properties of whatever grammar we write. This way the grammar is more succinct, more precise, and this way the grammar is actually part of what is known as a term algebra. Okay, anyway, we will not get into that. So
syntax trees may be different depending on the what if it is ambiguous, the syntax trees may be different for different cases.
Of course.
Then the meaning will be different.
No, but the point is that I am going to do induction on the structure. So if you want, you can assume that I have a fully parenthesized notation to get rid of ambiguity. Okay, his question was that, you can, if your grammar is inherently ambiguous, then you have more than one syntax tree for an expression, and that can change the meaning. That is true, but since I am not interested in the lexical aspects, when I say I am interested in syntax trees, what it means is that you can transform that syntax tree into a fully parenthesized notation using brackets. Okay, what I'm my rules, the rules of the game of semantic specification are going to be based on syntax trees in the sense that they are going to be inductive rules based on what is the root operator of the expression you are interested in, or of the syntactic category you are interested in. Yeah. So this, you can look upon this expression either as a fully parenthesized expression of the form e plus e with brackets, or you can look upon this as a tree whose root is the plus operator, and there are and it has two subtrees which are called E1 and E2, whose internal structure I am not really worried about. So each of these expressions you can think of as being specified in this form. Where E1 and E2 themselves are trees whose actual structure I am not interested in. That's how you do induction on trees, right? You do an induction. How is a tree defined? A single node is a tree given two trees T1 and T2 and a node with some label on it. The tree formed by T1 as left subtree and T2 as right subtree with that node as a root is a tree. And that's precisely what this is. Given E1 and E2 as trees, with the plus operator as a root, you get a tree. So trees are defined inductively, and we look at the inductive structure of the trees and not at the actual lexical syntax. If you want to clarify the lexical syntax for yourself, you can look upon this as representing this expression. Right? Fully parenthesized if you like. Right? So we are not going to be interested in ambiguity, we are not going to be interested in lexical matters, we are not going to be nitpicky about those various non-terminals which were important for parsing, like terms, factors, and so on and so forth. Yeah, we're just interested in expressions as a category. Right. So let's assume that we've got a collection script E, which is green in color because it's a forest of trees. So it's just the set of all abstract syntax trees of integer valued expressions. For the present I'm assuming that there are no identifiers, because we can deal with identifiers only after we have come up with a notion of an environment. So we'll do that later. For the present, just assume an expression language which does not contain any identifiers, and which does not, and since we are not interested in bracketing, it does not contain this production either. So it does not contain this, it does not contain this. Going back to PL0, identifiers, the identifiers in an expression could either be variable names or they could be constant names. Okay, but now when I get rid of these two productions, what I'm saying is I just have a pure expression language expressed in terms of the numerals. Okay, so the roots, the leaves of all the trees are just numerals. Okay, so that's my initial assumption, because identifiers really require the notion of an environment, which I don't want to get into now. Let me first tell you how to give a simple transition system for a language of just expressions on numerals. Yeah. So this brown n denotes the set of all numerals in the underlying machine. By the the underlying machine is quite down to earth, so it's brown in color, and by the underlying machine, again, I'm not saying that it's the bare hardware. It could be a virtual machine, which means that, as in the case of the PL0 compiler, the PL0 compiler is written in Pascal. So the virtual machine that you have got is a Pascal machine. So it's a bare machine with layers upon layers of software, the outermost layer of which forms the interface for the PL0 compiler, is a Pascal machine. I mean, so so it gives a view that what you have got underneath is just a Pascal machine with all the capabilities of Pascal and nothing else. Yeah. So there is this underlying machine which might be either real or virtual. Okay, but the important thing is that I am not interested in its architecture. Yeah, I am not interested in the details of the machine, except insofar as it gives me certain computational primitives that I can use. Okay, so in the case of an expression language, the basic computational primitives that you might require are well, addition of integers, subtraction of integers, multiplication of integers, and so on. Okay, so assume that those basic operations are somehow implemented either in hardware or in software in the underlying machine, which itself might be either virtual or real. Okay, so whatever is written in brown is going to be the underlying machine, virtual or real. It's going to denote an entity which really belongs to the underlying machine, and whatever is written in green denotes the language, a syntactic category of the language that we are interested in. Yeah, whatever is written in blue is part of the transition system. Okay, so the transition system for this language with no identifiers, which just works on numerals, is consists of a collection of configurations, gamma e, which is just the collection of all integer expressions. So it is just the set E, script E. The terminal configurations are all the numerals. Yeah, and for brevity, I will use this little o to denote a binary operation. So it could be one of these. Which are the binary integer operations anyway in the PL0 machine. Okay, and our underlying computational model assumes that these operations are already available. It is not a very unreasonable assumption. Okay, they are anyway already usually available in hardware. So I don't make any assumptions about the architecture except that I am assuming that the corresponding operations are already available in the underlying machine, and that greatly simplifies my transition system. If you want, what you could do is not assume that these operations are available in the underlying machine, but then you would go into greater detail about numeral representation, how addition is performed in terms of, I don't know, if you assume your numeral representation is purely binary, how is addition performed in terms of well, the Boolean operations and or and not. So you could assume an underlying computational model which just consists of the Boolean operations and essentially give us minimal specification of what an addition algorithm, of how an addition algorithm is implemented using those Boolean operations. Well, but then that is something you could do in your architecture or organization course. Yeah, but at this moment I am not interested in that. I mean, I would like to keep things simple for one thing, and it's not unreasonable to assume that these basic operations are already available in the machine. And so the basic operations that are already available in the machine will be represented in brown. So in particular, for example, I might make a statement like this. So this plus belongs to the language of expressions that we are interested in, that's why it's green. This plus is the operation in the underlying hardware. So it might either be implemented directly in hardware, firmware or software. I don't really care, and I don't really care how it is implemented as long as it's available. And the effect of performing this let's say hardware operation on two numerals is some other numeral, let's say p, right? So then this is this transition is something that acts as the basis for the specification of your transition system. You could go further and not assume this and further specify how each of these operations is to be implemented. Okay, so as I said, a transition system method you can go into great detail about everything. You can also perform abstractions. Here we are performing an abstraction with this assumption. Yeah. So the rules, so there are just 3 rules, well, not really 3 rules. So the basis rule is that assuming that this operation is one of the 4 operations which is already available in the machine is available, then this transition, note one of the things that we said was that we are looking upon this specification of a language as a form of symbol manipulation. That's how it can be operational. Okay, that's so one thing is that so I will assume that given 2 numerals, if given 2 numerals m and n, if m binary operation n gives me a numeral p, then in the expression language it also gives me a p. Okay, and what we are more interested in is in the high level language syntax. Okay, so but this forms the basis, right? So if E can go to an expression E prime, then M binary operation E can move to M binary operation E prime. This is another very simple rule. Okay, and if E1 can go to an expression E1 prime, then E1 binary operation E2 can go to E1 prime binary operation E2. Okay, so and in fact these are all the rules that you require for this simple language. It's a succinct and clear specification, but it contains a great deal of information. Yeah, for example, okay, let's do a little example. So with these rules, so consider this expression which has to be evaluated. Going back to what we said about expressions as a syntactic category, expressions just denote values or an evaluation mechanism, right? I mean there's no concept of store, there's no concept of environment, there are no complications associated with the expressions. But I've taken this so that it illustrates the concept of what are the transitions, what transition system rules look like, and what kinds of information you can derive from them. Right? So if you were to take this tree, so what happens is that I can derive, so from here this moves by a purely tree manipulation process to this tree, which is essentially that this 2 plus 3 has been evaluated and this subtree has been replaced by this node, right? Yeah, and if you move further, then what you have is this tree actually becomes this tree. Okay, so the only change is that this 1 plus 4 has been replaced by 5, and this, and so you go through this sequence of transitions. Okay, but the thing is that this example is not actually extremely illustrative. So these 4 steps actually are obtained in a form. I can claim that this step, this transition occurred because I can claim by rule E1 this, and therefore I can claim for the entire expression by rule E3 that this occurs. Okay. However, for example, I cannot, for example, consider an execution of this form. This is absolutely faulty. Yeah, And why is this faulty?
There is only one expression.
Huh, pardon? No. He says it allows only one expression. No, that's not true. Why is this faulty?
The operator is
1 plus 4 is not an expression all by itself. It has 5 minus 1 plus 4.
No, 1 plus 4 is an expression by itself.
But it is combined with 5.
so the two expressions must be disjoint and then there must be the other term must be
The
No,
operation is minus and we are doing
No.
it with respect to multiplication. This O is minus, should be minus because 1 plus 4 is the expression which is going to 5.
but why should this O that you are referring to be minus? Why can't it be star?
Because 1 plus 4 is going
because
to
they are
5.
1 plus 4
E1 is 1 plus 4.
Yeah.
Uh-huh.
I mean E2.
Okay.
So E1 and E2 must be disjoint and connected with a,
Sure.
but that is not so. It's very mixed up.
It's not very convincing to me. Oh, what you are saying is that I should have gone through several steps. Okay, what you are saying is that my first step should have been 1 plus 4 goes to 5, 5 minus 1 plus 4 goes to 5 minus 5, and 2, therefore 2 plus 3 star 5 minus 1 plus 4 goes to 2 plus 3 star 5 minus 5. Is it just that a step is missing in between, or is there something else? Yeah. Pardon? No, forget about the parenthesis. The parenthesis just is just a pure lexical matter. It doesn't matter. The parenthesis is just a way of specifying linearly what the syntax tree is supposed to look like. So
You need to completely evaluate the expression.
no, this our rules do not give complete evaluation. They give you a rule for a one-step evaluation, assuming that the underlying operation is available.
Like we are changing the expression on the right hand side, then the left hand side one should not be an expression, it should be a single item according to our rule.
Absolutely correct. So what he said was, if you look at the rules, the rule E2 specifies that you can take a right hand side operand, you can move a right hand side operand only provided the left hand side operand is already a numeral. The rule E3 does not specify, for example, that you can take E2 to E2 prime and therefore you can infer E1 binary operation E2 goes to E1 binary operation E2 prime. Nowhere is it allowed. And I have specified only positive rules. So whatever is, if you cannot derive whatever is not allowed, well, then it's not allowed. That's it. So for example, so this kind of a rule okay, so a rule like E6 is essential if you want to be able to perform that kind of reasoning. So the faulty reasoning that I showed can be rectified if you add this rule E6, which allows a right subtree to perform a transition in a whole expression, right? But supposing you allowed rule E6, okay, Then what is the problem? Supposing you, okay, so you want that kind of reasoning that we decided was faulty because the rules did not allow it, should also be allowed. So you add this extra rule which allows a right operand also to move. Then what's the problem?
So you can't terminate anything.
No, that's not true.
Have ambiguity. Which way to proceed?
No, ambiguity is a syntax. Oh, you have non-determinism, not ambiguity. Okay, then what happens is, given a complicated syntax tree, there are a variety of possible transitions it can take. Okay, and you no longer have deterministic behavior. You have non-deterministic behavior. In an expression language, if you allow this kind of non-deterministic behavior, then what can happen? Supposing you extend the language to include functions, this, that, high-level functions, what can happen? If you allow non-deterministic behavior, and it's an imperative language, and you allow functions, and you allow side effects, then it's not even clear that you're going to preserve any semantics. The results that you get from a program execution will be completely dependent upon at that point in what order the runtime system chose to evaluate the expressions. Okay, so at least from a pragmatic point of view, addition is of course commutative or whatever, but at least from a pragmatic point of view, it's necessary to be able to clearly specify an order of evaluation, at least in an expression language, so that there is no confusion later when you expand the language out. I mean, I might take the PL0 language and add more facilities to it. I might add functions to it. Okay, since you do not lose anything by specifying an explicit order of evaluation, it makes it convenient, pragmatic, and decent. It does not give an implementer arbitrary choices, or it does not produce conflict in interpretation. Right? I mean, you could add for the brackets and so on, since people mentioned it, you could add more rules. But the whole point is that it's not necessary. Okay, it very often just clutters up the matter at hand. So one possible way of defining this semantics in a deterministic fashion, and determinism is very important from a pragmatic viewpoint, from the point of view of an implementer of the language. It's also very important for a user in case the language allows side effects. Right? So in fact that is a problem with many of these Pascal implementations. You will see in a Turbo Pascal environment, for example, you actually can get a choice of menus on how you want an expression to be evaluated, in what order you want expression to be evaluated, but the manual itself is silent on that matter. And we should realize that especially in floating point arithmetic, for example, addition is no longer commutative, not even associative. Multiplication does not distribute over addition or subtraction. We lose a whole amount of mathematical dogmas we are brought up with when you do actual floating point computation. So sometimes, just for pragmatic reasons, it becomes necessary to lift these constraints to the level of a language definition, and at the level of a language definition you really do not lose anything by making it deterministic. It only helps the user and the language implementer to decide on a specific order. Yeah. So adding extra rules which allow non-determinism may also be very, very faulty sometimes. It's open to a variety of interpretations. Yeah. So in this case we have played, by having just 3 rules, we have played absolutely safe. It allows only a left to right evaluation of the subtrees, of the trees. So till you have reduced the leftmost subtree to a single node, you are not allowed to proceed with any of the right subtrees. That's what these 3 rules specify, and they specify that by default. What you cannot do is being specified by default. Right? So when you add a rule like E6, then you allow also simultaneous, for example, evaluations or independent evaluations of right subtrees. But these things, but adding such rules in order to presumably give more power to your transition system may not be, though well intentioned, might actually lead to flaws in the semantics of the language, flaws in implementation. If your underlying computational assumption is that there are an unbounded number of processors available to perform all these, sure, allow this too. If your underlying implementation is such that you cannot have side effects, fine, this is perfectly fine. But if your language is something that's going to have, so that's how a later feature added to a language can affect the complete semantics of a language. I mean, an expression language is actually trivial and simple and all that, but the point is that the amount of information that you can derive from this has long-term consequences on adding new features to the language, which may not be obvious initially. Yeah. So this, for one thing, it's clear and concise. Actually, this, since I have taken a shortcut in the sense that I have used this O to represent one of 4 operators. But as I said, since they are all part of the computational model and they are all readily available, it doesn't really matter. So you can look upon these 3 rules as really multiplied by 4. I mean, there are 12 rules, if you like, 1 for each operator, because this O is really not part of the language. Right? I mean, this O as an operator is not really part of the language. It's a meta variable for the 4 operators. Right? You actually have 12 rules, but it's concise, it's precise, it gives a deterministic order. So there is only one way a syntax tree can be reduced to a single node. Yeah? So what it means is that you have to craft the semantics very, very carefully, since everything that you cannot do is left unspecified. It has to be derivable from what you can do. Yeah. So now you can see that you can have a lot of trouble just crafting a few rules. It's not necessary to have a minimal set of rules. Just to play safe, you might add more rules, but then the consequences of that should be first realized. I mean, what does it allow? A kind of non-determinism? Is that non-determinism something you want? You might want it. I mean, if I'm designing this expression, the semantics of this expression language as part of an implementation for a machine like the Param with 64 processors or some hypercube, I might actually want that non-determinism. I might find it better to have that non-determinism in the semantics and get rid of side effects in function evaluation when I add functions to the language. I mean, I might explicitly ban side effects. okay, in the larger interests of program clarity, whatever. But whatever decision I take, I have to be absolutely clear. If there is some non-determinism, do I want it? In a multiprocessor environment, it makes a lot of sense to introduce these extra rules which allow left to right mixed with right to left and so on. But if your pragmatics is such that whatever you do for the multiprocessor machine should also be applicable for a uniprocessor machine in case you wanted to port the language, if your long-term view is of that kind, then you better think in terms of what are the constraints, therefore that then you better really worry about whether you want that non-determinism. Will having that non-determinism actually create problems, create more problems, or will it solve more problems? I mean, it could work either way. Yeah. So we will very often just take an implicit assumption that we want everything to be also implemented for a simple uniprocessor. But nowhere in the rules do we actually specify these things. In that sense, we are totally abstracted away from the machine, except for the basic underlying computational model. Okay. And it requires a really simple transition system, which seems so trivial, to actually drive home this important point: the difference between determinism and non-determinism, the difference between the desirabilities and the undesirabilities of the two things, the difference of how you should craft rules so that what you want, what you desire most actually is made specific in the rules. What you do not desire is also somehow derivable from the rules. Right? So writing semantics is no joke, even for trivial things. It's quite hard. I mean, which is one of the reasons why it takes so much time even to write a few rules. Yeah. Okay, so we'll continue with declarations and commands of PL0 next time. Thank you.